Hi. When starting out in the world of RF, one of the more confusing things to understand is the relationship between time and frequency and how they seemingly are opposite but intimately linked to each other. Well, I'm going to start off trying to discuss this question of what is resolution bandwidth, what is sample rate, acquisition time, and how it works out. But before I do, I want to get down to just something very fundamental that we're all used to working with is pretty much sample rate and how many samples do we get. This applies for both DAC or any other kind of data acquisition device. So what we're looking at on the screen here is just a very simple example of a modulated signal. In this case, it's an LTE signal. And we're looking at the same signal in two different domains. We're looking at it in the time domain and in the frequency domain, the frequency domain being up top. Now, if you look at that signal, you can see indeed it is occupying a certain amount of bandwidth. In this case, just about 1 megahertz, a little bit over actually. And what we're looking at is, in the bottom is really the time domain power versus time representation of that signal. Now, it's a RF signal, it's a complex signal, so there's real and imaginary, but we're going to stay away from that for the moment. We're just focusing in on the power relationship between what does a signal look like in time and in the frequency domain. So to start, we've got two sliders over to the left, real simple, IQ rate or sample rate and the number of samples. So we're just going to kind of move these around and look at the basic effect on the overall signal. So what we're looking at here is if we were to simply just go ahead and decrease the sample rate, or the IQ rate in this case, the complex sample rate, you'll note in the frequency domain that we start to lose bandwidth. It starts to go down. And at some point in time, we start to lose so much bandwidth in the actually acquired signal, we start to actually lose part of the significant signal content. And you can actually realize this by looking down in the time domain. You can tell the signal that we're looking at, although it's varying, really starts to look quite a bit different, to the point where if we really lower it down, not only does the signal portion look distorted, but also even the bursts that you're seeing later in time, which indeed are part of the signal, also you start to lose the sharpness of their edges because you just don't have enough spectral content to be able to acquire the full signal. So let's go ahead and move this back up to something that makes sense. That it really is acquiring the full bandwidth. And indeed, if we start to increase the signal to even a higher sample rate, you'll notice that well, we're starting to losing time. So why are we losing time in this case? Well, if you notice in all of these situations, we've had the number of samples to be fixed, and we're not adjusting it. Now, I'm also not scaling on the x-axis, but had I been, you would have seen that the time, indeed, would have been, as I decreased the sample rate, we would have been getting more samples. But we're going to go ahead and just kind of let that be fixed for the moment. So indeed, so we're losing samples because we're increasing the sample rate. So our time domain representation, we're just not acquiring as much time, although there's just the same number of samples being acquired. You can almost see that, as you can tell, as we get really low, the sample spacing starts to spread out quite a bit more. You can kind of see that variation just slightly, I guess, in this example. But let's go ahead and pull it up here so we're looking at the full signal. And indeed, as we start to decrease the number of samples in this case, we see the time domain. Of course, we're decreasing the number of samples, therefore we're getting less time. But an interesting thing happens up in the frequency domain. We're not getting the same type of frequency resolution to the point where we're not acquiring enough of a signal to actually be able to look at the different frequency components that make up that signal overall. And so we hit a certain point where what's happening up here is the spacing of each one of those parts is actually getting a little bit, as we raise it up, the resolution bandwidth, or the frequency resolution gets finer the higher we go in the number of samples here, because it can just determine the more samples that you have, the longer the time that you've acquired at a given sample rate, so it can actually determine the more spectral information. So I think this is something we've seen before, whether you've done audio processing or any other kind of just basic Fourier analysis, it all still holds true. Well, we're going to take that concept and roll it into the idea of what are the words and values that we work with when we're talking about more in an RF domain. So I'm going to go ahead and expand the window here. And you'll quickly see that we have two different values, or actually three different names, four different values, two different values for RBW, and we have span and measurement interval. Now, if we keep up with the frequency domain, you'll notice that the span kind of makes sense, and you can kind of see the correlation over here to IQ rate on the left-hand side. So as indeed we increase our span, the signal itself we do acquire a wider bandwidth of frequency content. And similarly, so if we want a finer resolution, if we want to be able to determine the power level of a 1 Hz and a 2 Hz signal, you need to acquire at least 1 second's worth of data. Similarly, so if the finer the resolution bandwidth we want, we need to start acquiring more data. And so you'll see that as we lower our RBW, the number of samples starts to come up on the left. Well, if you actually look down in the time domain, you'll see that correlation by the more that we actually acquire, the narrower frequency resolution, it requires us to acquire a longer period of time in terms of given samples. And so the resolution bandwidth has nothing to do with the actual span of the signal. That has everything to do with just the IQ rate when we're talking about it in the frequency domain. However, when we change over and we start to talk about it in the time domain, things get flipped around, as they tend to do when you actually compare and work between the time domain and the frequency domain. And so as I'm looking at it, if we just look at the time domain itself, as we raise and lower the measurement interval, you'll see very clearly it is a direct linkage to the number of samples that we have on the left and the measurement interval that we have over here. It's a very simple equation. However, when we change that resolution bandwidth, what is that thing? Well, in order to give a proper explanation, we'd have to go back to the architecture of your traditional kind of swept tune analyzer where this resolution bandwidth word came into play. But what you can think about it is really what is the span or the bandwidth at which I'm looking through to acquire, allowing my A to D to actually sample. Because my A to Ds are indeed centered at the center frequency, but it is the bandwidth at which I'm about to really analyze, or the signal that's about to be presented to me. So as I increase my resolution bandwidth in the time domain, it's opening up a wider window for me to sample with my A to D. So as I indeed increase that, you'll see that the span is increasing, and I'll go ahead and decrease it. You can see that that span is decreasing also in the frequency domain. This is all the same data being looked at 2 different ways. And indeed, as I decrease the resolution bandwidth, I'm not acquiring enough of the signal, so I'm decreasing that window that I'm allowing my digitizer to sample through. And indeed, you can see we're not sampling fast enough, and something as simple as those bursts that we were looking at over here, there's just not enough samples to indeed catch enough of that rising edge. So what do we do in any domain when we want to get more samples to catch a rising edge? We increase our sample rate, or in the RF domain, more commonly you'll see, we'll increase our resolution bandwidth to go ahead and look at that. But you'll see that it has that direct correlation with that IQ rate over there. So indeed, that is that basic byproduct of those two things. And you'll see as we indeed increase and decrease our RBW, our span is increasing and decreasing accordingly. So it's these two concepts that seemingly might be are very confusing, but at the same time, because they utilize the same names, and for good reason, for historical reasons, and it's not something that we're going to change, but we need to be able to work within and be able to recognize and have our minds think, am I thinking about a signal in the frequency domain? And do I want to set up a spectral acquisition? Okay, in that case, what do I want my resolution bandwidth to be? Well, that is correlating to the separation of frequencies, frequency kind of bins close to it, if not the same. And then what bandwidth do I want to look across? And that would be the span. Or if I'm saying I want to look at a signal in the time domain, what would be an example of a signal, looking at a signal in the time domain? Let's go ahead and scale that there. The example of a signal in that time domain would be I want to look at it power versus time, or phase versus time, or I want to demodulate the signal. All of those things are not necessarily looking at a signal spectrally, they're looking at the signal through time. And when that happens, resolution bandwidth turns into an effective filter that our A to D is going to be sampling through. Or we simply change our A to D sample rate in all of those cases. And of course, if you have a signal, why don't we just keep our measurement interval as low as possible? Well, sometimes you need to acquire the entire signal. In this case, we want to get all 4 chunks of the different bursts of information that we're looking at here of this LTE signal. So next time that you're trying to configure resolution bandwidth, be sure to ask yourself, am I thinking about it in terms of the time domain or spectral domain? And then kind of proceed forward from there, thinking about what the content of the signal that we're trying to acquire. Are you acquiring a 50 kilohertz signal or a 500 megahertz signal? And then set up, make sure that your instrument can indeed go to those settings that you need, and then go ahead and configure accordingly. And if anything, just kind of fall back on this video or any of the training material that you've had so far. So thank you very much. Hopefully this clarified it and it wasn't too long, and I'll hopefully be seeing you in the next video.